again, similar to last time, this is based on the slides from the last workshop, so that's why the name of my colleague is on there. Yeah, so networking security monitoring is actually very much into my research direction, so that's a topic I really like, and I hope you will all learn something. Short agenda, we'll first go over network monitoring, what it is, the overview, and how it can be achieved by NetFlow, and what you can do with that. Then we'll go over to intrusion detection, discover how intrusion detection works in general, how the intrusion detection system Zeek can be used, and also what honeypots are, and then we'll end the session with a short summary. So, this is the big picture, kind of, if you're considering the intrusion detection cycle, or PDDR, if you take the acronyms. So we have prevention, detection, reaction, and recovery. And as this is a circle, it comes back around every time, because after you recover from a certain incident, you have to prevent the next one again. So there are multiple parts in each part of the cycle, and we are mostly caring about the prevention and the detection part. So in the prevention part, you would have stuff like secure system design and IT security as you know it. Also network segmentation and stuff in this area. Also something like firewalls to prevent unauthorized connections between networks. Where the intrusion detection system come into place is actually in the detection cycle, as the name also suggests, and also honeypots, which are mainly part of the topic. So we are mostly working in this detection part of the process. We've also heard already about recovery and reaction in the other sessions. Of course, firewalls can also be a reaction, because once you react to a threat or to something that you discover, you can add new firewall rules to react before the next incident. Right. So, what is network monitoring? The first question we want to ask is, what do we actually want to know from network monitoring? So something like who accessed the resource, when, where, how, which resource actually is accessed, the performance and the quality. So it doesn't have to be only security related, it can also be just performance related. So how's my network performing, how well are packets transmitted, and also which protocols and services appear in the network. And now the question is, why do we want to know all these things? The first one would be intrusion detection and fault management, to see what's happening in our network from the security side. Then of course you can do analysis based on that. You can do monitoring, as I said, for reachability and availability, so that's more from a performance standpoint. You can also do resource management, so to plan the resources, how much resources do you need to allocate, how many services are requested and what capacity. And also performance monitoring and optimization. So while the network is operating, you can optimize flows, optimize performance basically. And the last one, which is kind of a little bit outside, you can also use it for statistics and metering. So if you have customers that pay for your network, you can of course bill them according to how much they're using. And for this you also need network monitoring. So as we care about the security part, our goals are basically to collect useful information from the network, and then use this information to manage the network into control zones, basically, to make it more secure. So you would first configure the device to actually emit these flow accounting records. We will see what that is in a second. Then you export these flows to a collector, so to aggregate all the flows that your network is producing. Then you of course receive the flows, write them to disk or to a database, and then you can do an analysis based on that. So you can have multiple collectors in the system. You can have something like a passive collector or a Unix host that can be at a mirror port of the switch and just receives all the packets that the switch basically handles, and then they're mirrored. But also you can have stuff like a dedicated flow collector that is inside the network and has its own database. And here you will see, for example, there's the campus network, and you would place the flow collector at the edge of the network to collect all the flows that are leaving the network. So all packets are forwarded there. and then you get flow records in the end. Right, and this is done via a mirror port, but this is very resource intensive because you, of course, mirror all your packets, which can be a lot. So on a network device, this is a little bit easier because the network device already handles the network traffic anyway. So here you have just a flow collector in the middle of the flow of the outbound traffic, and this can directly go to the flow storage. So you don't have to basically take all the data that build flows out of it because the network device already handles the flows and can do this for you. Now the question is, what is a flow actually? I've talked about that some time now. So this is defined as a set of packets with common properties, such as common packet header fields. So that means basically same IP address, same port, stuff like that. And depending on how narrow you define it, the flow can be exactly from one host to one other host on one port, or if you just say I want all flows from this host, then you can take all flows that match just the one part of the IP address, and just the source, for example. Right, so here you get your flow records from your router or from your network device that is on the left, and then the flow collector just collects it and stores it away. And then, of course, you can have your analysis part where someone is at this analysis station and then query that flow collector to perform analysis on that. But this, of course, needs device support from the device itself. So you cannot use any network router to do that. So especially the base or the cheap ones that are for end users that don't usually support this. And of course, it also has some impact on performance because the router has to do some copying, some duplication, has to export these flows, and this is basically performance that you lose, that you usually use for just packet processing. So it takes a little bit of performance impact, but not as much as doing it the other way around. So which protocols are there for exporting flows? Various vendors have made their own version of that. Usually we're talking about NetFlow, so this is just the first, I think it was the first implementation by Cisco, so it's very common. And they are all doing the same basically, but every company named it a little bit different. We will also see later on that they are compatible, so you can use hardware from Cisco and Juniper and Huawei and still have one flow collector that collects flows from all of these protocols. What is actually now a flow? I've already said it a little bit, but basically we're having just the key field of the connection. So source IP, destination IP, source port, destination port. Then you also usually include stuff like the layer 3 protocol, the TCP or UDP, and stuff like on which interface it was collected. So if you have a router that has multiple interfaces, multiple subnets, then this is also part of the information. And the TOS byte, I think, would be byte that's indicating the index of the connection in the sequence of connections. So here, for example, you have the source IP, I think the comma is wrong there, and the destination IP of some internal networks. So what can we do with NetFlow or with all the other variants that have similar names? It can be used for several applications. You can ask some questions regarding the IP traffic, because you have the IP information in the NetFlow part itself. So you can answer stuff like who, what, where, when, and how. For example, if you know which department is in which IP subnet, we just saw that here it would be 10.2.7.2, for example. Then you can see, for example, which user or department has been uploading or downloading the most, because you can just count the flows from this subnet, and then you see already who's that. You can also see which are the most commonly used protocols on my network. This one was just TCP/IP. You could also include higher level protocols like HTTP, FTP, whatever. And then you also get those statistics to see how much of my traffic is actually what protocol. You can also, to some degree, do identification of anomalies and attacks. We'll see how that works in a minute. But also you could do more fine-grained visualization, just export some charts, export some pie charts, for example, some columns, some tables based on that. So you don't have to look at the raw net flow data, but you can see nicely and user-friendly what's actually happening. But there are things that you cannot achieve by net flow monitoring, and that's why the second part of the presentation is about intrusion detection. And we'll also see what that is. So here we can see how we can identify a DOS attack on a router via net flow. So there is some estimated bandwidth here, but that's not so important. But here you see basically what happens. So there's the source interface, and the destination interface is given. So that's the router seeing where the packets are coming from and where they're going to. And then you can see also how many packets there are and how many bytes per packet there are. And as you see, this is all static, it's all the same value. And this indicates a DOS attack because you have some PC on that source interface here, always sending a single packet that always has the same length and all goes to the same destination interface, and also here the destination IP address. So all these packets basically try to DOS that specific host, because usually you would not have exactly this like the same packet size everywhere, and this really looks like it's a DOS attack. So they have some, usually these DOS attacks have, as I said, some of the same net flow entries. Sometimes it's even the same source IP address. In this case it is not, but it's always the same destination IP address, of course, because we want to DOS that certain host. And usually they also, as I said, have the same properties here. Could also be something other, some 80 bytes per packet, but then it would be always 80 bytes. And also what you can do to detect this, so this is basically some kind of query language, I think maybe from Cisco, that then, oh no, that's just a command line. So here you're on the router and you can do something like IP cache flow and see all the flows that are related to this IP. And then you can look for, and then you into the destination, so the service where you're actually concerned it might be under attack. In this case, this would be this IP address. And then you can see all flows related to this IP. So if in the previous example we had other flows, they will be excluded now. And then you can look for some attack signatures, as I said. Could be something like a certain port, could be something like the same packet size. That depends on what attack you actually have. So here, for example, they are all filtering on this port 666, and then in hex this is this value, and here you can then see all flows that use this port. So I talked about analyzers and collectors already for net flow. What should they actually support? So they first should be able, of course, to receive flow records from the exporters, so from the network devices that are in your network. They should be able to analyze these records to produce some new information based on that, and of course present these results in a user-friendly way. Some examples that exist, and I will show you some of them on the next slides, are named here. So I think some of them are proprietary, some of them are open source, but yeah, there's SolarWinds NetFlow Traffic Analyzer, some network monitor scrutinizers, also popular, I think, and Nprobe and Ntop and G. And they also mostly do the same. So here, for example, you scrutinizer, you have these nice user-friendly visualizations that I talked about. You can see some graphical representation of the network, so where are the flows going, which hosts are actually connected. You can see stuff like which applications are present in your network, so depending on the port and some other data, you can also get that from NetFlow. And here I think it's something like office camera, SMTP, so it's yeah, a little bit difficult to exactly sometimes know what application there is. And also some other statistics like, I think this is the overall usage, and yeah, some other statistics. And you can already see a trend, so the next one, Management Engine or Manage Engine, looks similar. I feel it's a little bit nicer, but it's actually the same. So here you have a heat map to say which kind of connections or flows the tool detected. So here it can already decide between something like clear and critical. Maybe it's doing some analysis based on what we saw already. Also, it can produce some kind of alarms similar to that, and also something like how many IPs there are available, and because based on the net flow data, you can then see which IP addresses are producing traffic, and this can also indicate which IP addresses exist in the network at all. And again, this SolarWinds thing is again similar, so you already see pie charts are very popular. Again, with applications here, you use something like, this one's a little bit more detailed. It says something like just an HTTP, but also SQL server or Oracle database, so you can detect this a little bit more accurately. And here you can also see that you can integrate multiple sources. So here we have some Juniper hardware. These are the sources that the tool knows, so all the network devices that actually send the netflow data. And here you can see that there's a Juniper part, a Juniper device, some Cisco devices here from the logo, and a Huawei device. And they all export to the same collector, and you can then just have statistics across them. And here's also something like utilization, so this might indicate that you have to provision a little bit more bandwidth if something here is all the time high. So okay, now we saw that you can use NetFlow. Okay, we have some monitoring and we can detect some attacks, but of course, as the talk suggests, this is not sufficient. So again, this is what we previously saw, and now we will talk more about the detection part and a little bit also about firewalls. So usually you're talking about intrusion detection systems. These are systems that do not only work on NetFlow, but most of the time just on raw data that they receive. And if you combine that with a firewall, so you say if the intrusion detection system detects something that is malicious and you then issue a firewall rule that blocks some traffic, this is then called an intrusion prevention system. So an intrusion prevention system is maybe a little bit on both parts of the cycle. It's prevention and also detection. Or maybe a circuit would also go like this. So this firewall, so you react to the threat. So our overall goal is actually similar to the network monitoring part, but here the focus is more or less only on IT security, so you don't usually care about the quality of service or your delay. You really care about intrusions, which is an attacker that is of course in your network, and misuse. So there could also be some internal person that maybe is not an attacker, but uses their resources wrongly or uses more resources than they're allowed to. So, I mean, the question is a little bit self-explaining, I think. So, why detect attackers? I mean, of course, we want to detect attackers. But the first part is really critical here. Full protection is usually not possible, and the usually can actually be removed. So, full protection is not possible. You can have as many protections as you want. I think that's also what we had in the previous talks. There will eventually be someone who finds a way around all your protections. Or maybe it's an insider attacker who just is behind the protections already. So you need to also have protection afterwards. You need to be able to constantly try to detect these attackers, if there are any. And usually, even though there are some other measures that you could have taken, usually you don't take all the measures because it's too expensive. So of course you can segregate the network very detailed. You can also define firewall rules that really only allow connections that are actually useful and allowed, but that's usually too expensive, and you usually don't do it to the very last level. And in the end, you also need hardware that supports this. So you need an ASIC or a chip that is really being able to, in a firewall, for example, handle all these restrictions that you throw at it. And also sometimes, I mean, the list goes on, but some other thing that we often see, especially for medical systems, if you remember the ransomware part, sometimes there are systems that should be patched, but they are not patched, and that can have reasons can have compliance reasons. So at a company where I worked, there was one single Windows 2000 machine, so this is some years back, but they had Windows 2000 running on it, and because they used this one obscure program for one task, and this could only run on Windows 2000, and even by that time Windows 2000 was not supported anymore at all, but they had it very isolated without network connections just to run this single program. And of course, this can always happen, and this is always kind of entry gate for attackers to enter your network. So there are many more reasons, but usually this one is most important. Like there is no full protection, you need detection. Yeah, that's it. What can you achieve with intrusion detection? So of course you can detect attacks and attackers, but you can also detect basically the misuse. So a legitimate user might use something that he's not allowed to, or that be more resources than he's allowed to. So now we are of course in this step, as we saw previously, and that's also important. If you don't have the cycle, if you basically only have the upper part, you say, or if you only have detection and say, okay, we detect attackers, that's enough, that doesn't make sense, because if you detect something, there need to be consequences. You need to somehow react on that, you need to issue new firewall rules, you need to, I don't know, if it's a company, if it's a legitimate user of the company, you need, yes, there need to be some consequences. You cannot only do detection and then react, basically. And some goals for that could be to limit the damage, of course. If you have some automated response mechanism, so you can maybe isolate a certain host that you detect, or just prevent him from doing more damage. It can also be just to gain experience on the attack. The next one. So, the third one could also be if you want to deter other attackers from attacking your network. You can achieve this by actually arresting other attackers. So if you collect enough information that you can actually arrest someone, then of course you can maybe advertise this and say, we got the hacker that got into our network, and maybe this will repel other attackers that maybe thought about attacking your network, but then they don't do it because they see that you actually catch other people. How does this intrusion detection system more or less work? So you have some events that are coming in. That can be different types of events, and we'll see what that is. They will be collected at the terminal or some kind of sensor that catches them. That can be network-based or host-based, which we will see. And then they are logged into the intrusion, or into the central intrusion detection system, or SIEM is another term that is similar. And there you have some part that detects something, so some algorithms that basically take the events, work with them, analyze them, and detect something. And then sometimes also the reaction is included. So as I said, if you have an intrusion prevention system, new firewall rule is added, and then you somehow limit the damages that you see. So that can achieve an automatic reaction, and that of course influences the events that you get. Sometimes you also, or usually you also produce an external alert, so that can be an email, an SMS, whatever, something that is then emitted to say, to your security officer, there has been an event detected or an attack detected, and you should do something about this. This is especially important if you cannot do automated response, because someone needs to know, someone needs to address this issue basically. So, right, you record all the events, you perform analysis, and then you report the attacks. And sometimes also with countermeasures. So what is this audit data that we're talking about? So it's the recording of security relevant events. That can be something from computer systems. So if we're not talking about network, if we're talking about a single host, that can be something like opening a file, executing programs, detecting some access violations. So someone started something that needs administrative rights, for example. And also something like failed password verification, if someone tries to log in and that doesn't work. That's all something that is happening on a host, and this is maybe part of an attack. So maybe the execution of a program can be, for example, an attachment that is from a phishing email. So this is also something we want to detect. From a network point of view, that's something different. So here you have all these connections and flows you basically see. You're not on net flow level, you need to have the explicit packets, so net flow is not enough. It's not enough if you see a connection from A to B. You need to know what other packets, how do the packets look, maybe is there what protocol is there besides TCP, is there TLS, is there something else? And these actual packets that are transmitted may also contain more information about the attacker, for example, or especially if this is not encrypted. So if you're not using something like HTTPS, if the attacker tries Telnet, which is unencrypted per default, then you need the raw packet data to see actually maybe what usernames he tried, something like that. And also it can be something like app-specific events. So if you have certain services or apps in your network, they might also have something specially related to that. So if you have an app on your device that is not the system basically, but for example on a smartphone that has also some kind of login mechanism, then of course there is no login on the system level, but there is a login for the app itself, and this could also be an event that is then sent somewhere and processed and used for intrusion detection. So you have different kinds of events from different sources. And they all are the input for the intrusion detection and response mechanisms, and this means they usually require some integrity protection. Because if you don't have integrity, then an attacker can just send wrong information basically and distract the intrusion detection system. So you don't want an attacker that can send arbitrary packets to your IDS. So because then if they know what IDS is running, what algorithms they're running, they can actually defeat the IDS maybe, and this is something you don't want to have. So what do we actually want from an IDS? So what are our requirements for that? This is the usual confusion matrix when you're talking about something like a classifier. So you have true positives, false negatives, and true negatives. And if we're mapping this to the IDS problem space, then here you have the event nature. That means, is the event actually anomalous or not, or normal? So is it an attacker or is it a normal event? And then here you see what the detection basically produces based off that. And of course, ideally we want to have only this one, right? So our anomalous attacks or our attacks, they are classified as an attack, so it's true positive, and our normal events are classified as normal, so that's a true negative. But of course, as usual, it's not always the case, so usually you have some false negatives and some false positives, and both are bad, because if you have false positives, then you maybe react to something that is not a threat or not an attack. But if you have false negative, it's even worse, because then you don't see an attack and you say, oh, that's normal, we don't have to do anything. And this is the reason why you have then these numbers like we saw in my previous talk yesterday, where it says like usually an attacker is for 200 days in a network until they're discovered, because you have some false negatives or a lot of false negatives and you don't actually see the attacker. So what we actually want to have is high accuracy, so that means less or low rate of false positives, low rate of false negatives, so actually only true positives and true negatives. Exactly, that's what I just said. So the false alarm we want to avoid, and the attacks that we're not detected, of course, we also want to avoid. Also, an IDS should be easy to integrate into a previous system or into a network. So that should not require that many modifications. Similar to NetFlow, where you can just take a device that is NetFlow enabled, or maybe switch out a device to something that is NetFlow enabled. You also want your IDS to be basically like a plug-in solution. You just plug it in and then you have IDS. It should also be easy to configure and maintain, because you regularly need to update it, you regularly need to make changes, need to maybe change your algorithms, change your thresholds for some detections. And if that's every time, for example, you have to reboot the whole network, then it's not going to work. You need to have something easy, something maintainable. It should also be autonomous and fault tolerant when it operates. So it should have something like a redundant power supply, for example. It should have something. It should be autonomous, so it shouldn't need human input. Of course, when an attack has happened, someone needs to do something, but usually just for the IDS to work and to detect, there should not be any human interaction basically required. Ideally, it also should have low resource requirements, so you don't want to have to buy a huge server to just pull in your network, just intrusion detection. So usually you want to have low resource requirements there, so you can actually just buy a small machine, put it next to it, and have some intrusion detection. And it should be self-protecting, so it should not be able to be deactivated by an attacker. Similar to the integrity protection we talked about. If an attacker can manipulate your IDS, then that's always bad news. Especially because usually then they attack even more because they can defeat the IDS. If you're talking about a specific IDS system, there are multiple ways you could talk about it. First, you could talk about the scope, and we already saw that a little bit in the sources part. So you can have a host-based IDS that collects information from a host, like opening files and processes. You can have something network-based, that would be something that really looks at the packets, looks at all this information there. And you can have, or you usually actually in practice, you have hybrid versions that use information from both, correlate them, and especially gain new insights based on both sources. And if you're talking about the architecture, you can have something centralized, so just a single point where all data is collected. You can have something hierarchical, so it's aggregated on top of the tree, and then you have, eventually you have one thing at the top that collects all information, or it can be distributed, so you have some sensors that are somehow a little bit more autonomous. They exchange information between another, and but can also do analysis based on their own. They don't have to report to a central point. And also, if you're talking about the detection mechanisms, there are multiple ways. So you can have something that is signature-based. That would be something like your usual antivirus, for example, that just has a signature that knows, okay, if I see this pattern in an executable, that's bad. That, of course, is good because usually it has a low false-positive ratio. If you see something that has this signature, then it's usually really a virus or something bad. But of course, if you have a new threat that you don't know, then you don't see it because you don't have a signature for it. Then there's something that's policy-based. That means basically you define what is allowed in your organization, and everything that is something else is usually malicious or not allowed at least. And then you have anomaly-based, which is basically the other way around. You learn a model, usually as machine learning does it, to know what's normal, and then everything that's not normal is basically classified as anomalous or as malicious. So here the scope, as I said, the first one would be analysis of system events, so files, processes, sockets maybe also. The second would be network-based, so really looking at the IP packets, what protocols are there, what payload is there, if you can see it, if it's not encrypted. And usually you have the hybrid that is combined. For the host-based detection systems, there are multiple ways to actually get the data, so which processes are open and stuff. Usually you work on logs provided by the operation system or by application logs. You can then, for example, Linux offers an audit interface where every action, every system call that is performed is logged. You can then take that source of data and basically ingest it. You can easily detect insider attackers, because if a user that is legitimate modifies a file that is maybe part of an attack, then you can see that. You can see illegal access to files. If a user tries to access something that he is not allowed to. You can also see something like Trojans or rootkits that are installed, because you see what files are executed. You can then do maybe some signature checks on that. And but of course it also has problems, because you have to have that installed on every system. So every host in your network has to configure all. It has to configure all these events. It produces a lot of information. So just imagine if you're using your regular PC, how often do you open files, like constantly, and all of that information is then processed. So that takes a lot of processing power to analyze all that. And the reason or the result of this is that you often don't do real-time analysis, but rather if you see something somewhere, you then look into the data and say, okay, let's look back what actually happened there. So you just store it away, and later on, if you need it, you just look at it on demand for a certain time frame. And of course, that's hard to manage for a large number of systems. So that goes against our requirement of being easy to maintain, basically. You have to, if, for example, a system update breaks your audit log, then of course your whole RDS, this part breaks down. And this is why you usually have it on only a small number of hosts, and do the hybrid analysis with the network part combined. One example for this kind of software would be Osquery. That is something, an open source tool written by Facebook originally, but now it's I think maintained by the community. And it basically works like this, that it builds a view of the operating system in an SQL-like interface. You can do something like, you can see it very, very badly at the top. It says something like select UID name from listening ports, process where PID lies something. So you can really equal to something. You can really do something like an SQL-like query on your system, and then this query is lively or real-time executed on your system, looks at all processes that are running, looks at the sockets, and then reports the results. That's very convenient because most people know SQL, and you can really easily It's fast and it's beta tested, so it's actually deployed in real companies, and this SQL view is built to be very, very fast. And here you can see just a number of things that are supported. So each one of those is basically a table. The table of processes has something like the PID, so the process ID, name, path, but it even goes further with Linux parts of the user ID, the group ID, the size of disk, the system time that it took to execute. You can also do something like detect high intensive processes, that all works. And the same one, you have something for USB devices, logged in users, so everything you can imagine basically about a host, you can query. And the good thing is, because you only write the query, it only then executes it. So you don't have to collect all the information. You can selectively write a query that just says, okay, now I'm interested in processes, because that's something that maybe is critical right now, and then it only does this. And you don't have to configure your system to log everything, and that's really what makes it scalable. Right, it's independent of the operating system, software, or hardware, so there's versions for Linux, Windows, and macOS even, and I think they're also working on going to mobile with it. It's basically run as a daemon, so you just have your Osquery daemon in the background, and you can then, from a central point, schedule your queries on it, and it can do a lot of stuff in regards to aggregating, so you can have your periodical queries that come back every minute or so, and your results are aggregated, and you generate logs that see also what changed. So you can see how many new processes are spawned every second. That could also be something that's anomalous. Yeah, it's very, very configurable in that way. And basically, to sum it up, it's a cross-platform operating system instrumentation framework, so a very, very long word there, that can be used for intrusion detection, as we saw, but it can also be used for something like, again, non-security stuff, so infrastructure reliability, how reliable is the system performing, or something like compliance monitoring, so are there only processes executed that are allowed, stuff like that. So it's not only a security tool, but rather a generic monitoring tool in that sense. But the important part is also, there's no intrusion capability of its own, so you can write queries, and these queries are executed, but it doesn't know what these queries mean. So usually we have something, some system, some analyzer somewhere else that takes this information and then does something based on it. It does not do any signature checks or something like that. So now this was the host part, and Osquery is just an example. Now we come to the network part. Here you mainly work on packets sniffed from your network layer, so maybe just duplicating them. And usually the systems that are in place use a combination of something like signature-based. They use protocol decoding, so they know what is the TLS header, how does it look like, what's a DNS packet, how can we extract the information that is actually relevant. And also sometimes they have something like statistical anomaly analysis, so we have not seen this kind of packet for the last weeks, maybe it's anomalous. So that's usually a combination of those three. And this is just some examples that usually network-based IDS can detect. You can detect something like buffer overflow attacks, if there's really an uncommon way of, like, for example, you remember Heartbleed, where all this information got extracted from the server. This is something network IDS can very easily see, because you can just look at the packet, can see, okay, this value here is larger than the rest of the packet, this is not allowed, or this would result in buffer overflow, and this can be detected. It can also detect invalid packets, so if an attacker sends a packet that is just not according to the protocol, then this is also recorded. And also something like attacks on application layers, so is this a malicious HTTP request, for example, something like a DDoS, because you see all the packets, more than NetFlow even. Spoofing attacks, so for example you can see that the IP of a certain device, if you have, for example, MAC addresses, that often changes, that can also be an indicator. And of course something like port scans, so if you see one IP address that has a lot of scanning activity, it scans either a single host or multiple hosts, this is something you can very easily see, because you just count the scans per IP and then you basically see it. And it's often used on some so-called network hubs, so usually you would place it at the edge of a subnet, for example, and the router is connected to the rest of the network, because then you can see everything that's happening in the subnet. and then yeah, you combine all the sensors that you have to have a complete overview, basically. So this is how it could look like. You would have your internet, your network somewhere below, maybe something like a DMZ, so a demilitarized zone, that is like not behind this firewall, and then you have a switch here and a switch here that both monitor or forward their packets to network IDS, and so you see what's happening in this network, in this part of the network, and you can see, of course, what's going to the internet. You can also have something on your last gateway to the internet, basically. So if you have your edge router somewhere that is directly connected to your ISP, here you can also monitor stuff, but of course you don't see some connection that's going from here to here or the other way around. So you only see outbound, inbound packets, but that can be interesting for different reasons. So you can see your load, you can, the problem here is that you have a high load because of course all traffic that goes to the internet goes through it. And that also usually results in a high rate of false alarms because you just have so much traffic, and your algorithms more often produce something that looks like an attack but is actually not. Here in the DMZ it's a little bit easier because of course there's less data and you have a segregated network, and it can only of course detect attacks on these devices. So if an attacker attacks another device, then of course this monitor will not see it, but it could also reveal compromised devices on that network. So if you see someone here, some like web server who's doing some requests that it should not do, because the web server usually only receives requests and then answers, but if this web server does something that talks to here, for example, then this is of course malicious. Usually it looks like something that may be an attack. Or if you're in a LAN here, of course they again have low load, and you can again, similar to here, basically see a compromise between these hosts there. So there are multiple ways where you can usually use a combination of all these. So you have all three of them maybe, or this one is maybe configured a little bit to be not so critical. If there's a false positive, so you say, okay, we see something but we do not really care about it. But usually if you detect something here or there, then this is usually a high alert and you should react to it. And then usually you have something like a hierarchy or central point where of course all these sensors talk to, and here you do your central analysis, you see what's happening and you combine all the information. So again, now to the architecture part, I already briefly talked about it. This is how it would look like on a topological level. So centralized is basically what we saw here, right? Everyone's talking to the central unit, kind of a star topology. Then the hierarchical one is similar, but here you usually do it like this, that the lower ones are actually the IDSs, so they get the data, and the upper ones are usually not full IDSs, but rather just analysis units. You forward it, analyze it somehow, maybe calculate some intermediate results, and then you bubble it up, and then of course the most critical alert can be then generated here because again you have all the information. And where research is going, or where actually all the vendors are also going, is distributed ones, because usually all this doesn't really scale, right? Because if you have a lot of alerts, a lot of events, then if you go to the central part, then you have already lost, because the central units cannot handle it. If you do it hierarchical, then it's a little bit better, but still all the data goes to this part, and you have still problems because the load is too high. And in a distributed way, you exchange between the different IDSs. But here the problem is, of course, you need to know who do I need to share this information with. So if this one detects something, where do I send it? In this picture it only sends it down below, but maybe it would also have to send it here, because part of an attack is also seen here. So a lot of the problems in this area, that's where research is also happening, also my research actually, is to make this structure as efficient as possible. So keep the information that is transferred low, but also know where the information actually needs to be shared. And actually there are also some attacks that you cannot really detect in this way, because if your port scan, for example, is distributed over multiple hosts, and one is mirrored by this, one by this, and one by this monitor, then all these three need to communicate to detect this attack, and if you don't have this, you cannot really see an attack. So usually, currently there are versions of this deployed, but the push from academia and industry is to go more towards distributed, to be more scalable and more resilient to attacks. Exactly, and the question is basically how do I correlate events in a collaborative scenario, because here you don't know who you need to collaborate with to detect it. Then to the detection mechanism taxonomy part. So here I briefly said already, signature based is very, very strict. So you just say this byte sequence maliciously detected and we're done. Policy based is really you don't really put in what's normal, you put in what is allowed. So you have a set of company policies that say connections from this subnet to this subnet are legitimate, the other way around not, basically. Or for example, and then the policy-based IDS can just easily look at any connection and see, okay, is this allowed, is this not allowed, and then you just, if it's not allowed, you get an alert. But usually the problem here is you don't have policies that are that detailed to every last level. So you know, okay, connections from here to there are not allowed in this network, but what if there's some special scenario where the maintenance guy who has to do some remote administration does a connection? And then in this case you get an alert, although it's still a legitimate maintenance thing, for example. So usually your policy is not as fine-grained to define every possible scenario, and that's why in this case you still have a lot of false positives, or also false negatives, because you don't know if an attacker maybe does something that looks legitimate. And anomaly based is basically again the machine learning approach. We just take all the data that we have and say, okay, we think in this scenario, in this case, there is no attack happening. Then we learn some kind of model based on that, and then we can detect anomalies. But here again, there's also a problem, usually because humans are so unpredictable, and if you have a regular network where humans are interacting with machines, it's very, very hard to learn a model that is completely covering the regular day-to-day work, basically. And usually you learn some reduced model for some parts of an attack, but because sometimes maybe the one day I'm just using Firefox and googling around for some stuff, the next day I'm on Stack Overflow and looking on coding examples, and on the third day maybe I don't know, coding something in Visual Studio that has different events that are produced. So you cannot really learn a complete model if you have a network of people. And that's why this is also problematic. So usually you have kind of a hybrid approach that you do some signature-based stuff, some policy-based detections, and also some anomaly-based detections to achieve best results. That's basically what I just said. So we have these attack signatures, and we'll also see that in the next session with the hands-on part, where we will actually detect the attack signature. This is a sneak peek. And then, you basically check your events if the signature is in there. You can also, how you get to a signature is basically you analyze vulnerabilities. So in the case of heartbeat, for example, you would see how heartbeat is actually exploited, and then you can derive a signature based on that. And then you can also go back in time and see look at your previous events and see if the signature has matched any time before, although you didn't know it until that time. It's a little bit hard because, of course, you have to specify these attack signatures, and you have to constantly basically update your signature database. But usually most IDSs that support this have some kind of language for that, so you can really easily describe how a signature looks like. Drawbacks, I already said, you need to prior knowledge, you need continuous updates to stay up to date to the current threats, and you have a high rate of false negatives if you have not updated for a week, for example, because then of course you miss a lot of attacks. Snort is one of the most well-known signature-based IDSs on the network level, and you can see kind of this language that they describe. So here you have something, okay, what should happen if this rule matches? In this case, an alert should be generated. To which kind of things should apply, in this case IP packets. Then here you can specify the source IP address and port. Here it's any, so you just say, okay, I don't care what it is. Same for destination IP. And then what should happen, and here in this case, the alert should contain a message that says this is an IP packet. Of course, for a real rule, you would then update this and maybe also look at the contents of the packet. But basically with this language you can make it very easy. All in all, it's actually an IDS and an intrusion prevention system, so you can, as a result of this rule, so here it's just an alert, but you can also write a firewall rule and then block traffic. And the good thing is, because it's signature based, it's very fast, and you can actually do it in real time. So all these rules are very simple and built in a way that they can be easily checked on your packets that you receive, and this is why Snort can achieve real-time operation in this case. Yeah, each intrusion needs a predefined rule, so if you have an attack that is not based on this rule, then you don't see it. And this is the rule itself. Then we go to policy-based detection. Again, it defines what is allowed, or maybe sometimes what is forbidden, but usually what is allowed. A violation creates an alert, and that's similar to a firewall, just not a little bit softer, right? Because if the firewall detects something that's not allowed, it just blocks it, and here it will create an alert or maybe notify someone. Yeah, again, drawbacks need a lot of configuration. Usually you don't have that, you don't know actually to the lowest level what happens every day. And you need expert knowledge of all the systems that need to be protected. And for example, if a new service is started, maybe then your policy previously didn't allow it, and then you need to update all your policy rules to now handle this new service that you have to deploy. For policy-based detection, one example that we also used hands-on is Zeek, that is previously it was known as Bro, and this is basically a real-time network analysis framework. So you can write very complex rules and basically handle them in real time. It's primarily a network monitoring tool, so it captures or can do protocol decoding and all that stuff. But it can also be used for pure traffic analysis, so you don't have to do intrusion detection with it. But it can also be a powerful intrusion detection system if you write the correct scripts. The architecture works like this. So here in the lowest part you have your packet stream. So these are really network packets that are mirrored from a switch or a router. Then the PCAP is basically a library that is able to pass these network information. You receive then this filtered packet stream in your event engine, and this is basically the core part of Zeek. So that's an engine that continuously generates alerts, events. For example, if you see an FTP packet, because that is here parsed, and you see, okay, I see the header is similar, or it's actually an FTP packet, then an event is generated that says new FTP packet. And then of course, if you see in this FTP packet, there is a vulnerability, then you can generate a new event that says, oh, FTP vulnerability detected. So everything basically works on this event engine, and is constantly new events are added. Then these event streams are basically executed, and for each event you can have a script that handles this. It says, okay, if this happens, then do this. But the fun or the good thing is, the event handler, basically as we define it, can emit a new event. So you can have basically, that's why it's a loop here. You can detect something in an event handler, see, okay, that's an FTP packet, I analyze it now, and then generate a new event that is then again handled by another handler. So you can have a circle here. And if you want to have generated an alert, so you see, okay, this is now a vulnerability, something that's exploited, we need to alert someone, then you can do real-time notifications, or also just write it to disk and say, okay, this is an alert that we saw, and someone needs to look at it later. So there's a feedback loop kind of that also goes back down. The focus here is on application level semantic analysis. You don't look at TCP data, you look at FTP data, HTTP data, DNS data, something like that. It's policy based because you have to write all these event handlers yourself. You have to decide what should happen if something is observed. And also it can track information over time, so you can count, for example, the number of FTP packets, the number of DNS packets, also per host. Yeah, it's really flexible there. And in the intrusion prevention part, because you can also instruct your firewall to log something, it can also act as a dynamic, intelligent intrusion prevention system, basically. So this is how it works. So you have a network below. There is a tab, which is the mirror port, where you receive all your flows from. Then you have this Zeek platform, that is all this basically in the middle. That includes packet processing, so it extracts protocol information. That includes actually a whole programming language, which we will see in the hands-on. So that's a complete programming language for network monitoring, and it includes a standard library of various functions that you can apply to program your scripts. Basically, so you can write, you can detect what protocol is in protocol is on a packet. You can have data types actually for all these network events. So there's a native data type for ports, including the protocol. There's a native data type for an IP address, which you don't usually have in a programming language. And all this allows you to write apps or scripts based on that platform to do something like, and here intrusion detection is just one example. You can do traffic control, file analysis, compliance monitoring, everything you want. So because you have this whole programming language to actually at your disposal, it's really flexible at what you actually want to achieve with it. And how can you use Zeek to understand your network? So actually, if you have just this log file that Zeek produces, in this case it's called files.log. It's one of the many files that Zeek per default just writes. You can then use just regular Unix command line tools. So here that's just a tool from Zeek to cut out a specific column, and then you can do sort, unique, count, and then sort by number basically, and that would enable you to do something like this pie chart where you have, okay, octet stream happens sometime, but the most part what we see is text plain, sometimes maybe also some images. So it's very command line heavy, so there's no, by default there's no graphical interface, no fancy animations, but because everything is contained in these log files, you can write this can also be automated then, you can write your scripts to basically produce updated pie charts or some other languages. So this would be, for example, the file types that you see transferred to the HTTP. Also you can do something like the software analysis, so even though Zeek is network-based, it can also detect basically the user agent. You can see this is Firefox or this is Safari. It can also detect something that is Windows update traffic, so there's also some rules there. And similar to last time, here we look at a different log file that's called software log, and we do the same. We cut out host and name, then we sort it, we count it again. Here you just extract again the second part, and then you see how much this software was applied on all hosts together. So if you know these command line tools very well, then Zeek is very, very nice to you. Let's say it that way. And then finally, anomaly based detection. Again, yeah, we want to detect behavior that differs significantly from our normal use, from our model. But this implicitly says that we have some expectations to our users. So we expect them to have certain patterns, certain normal, regular behavior. They usually, in the morning, they always open Thunderbird or Outlook for their emails. They usually open Firefox at lunchtime because they are bored, something like that. And the whole system kind of breaks down a little bit if these assumptions are not valid anymore. Right, so the general assumption is that your normal user behavior, so to say, can be described in a statistical way. That requires some kind of learning phase, as always with these learning approaches. So you have to have some part of traffic or some part of operation where there's normal activity, and then that specifies what's actually normal. And the problem is usually you require your data to be labeled, so you have to know this is a time period where no attack happened. But the bad thing is usually you don't know that no attack happened at all, so you need to have labeled data, as usually for machine learning. And that's very hard to obtain in this scenario because you usually do not completely know what happens in your network. Yeah, the analysis part then just compares your recorded events with the reference model that you obtain. So here you would see that our normal clusters basically of some abstract clustering function result in this model of these three clusters that we usually expect. And then here we see, or these two actually, these are labeled normal. And here we see some outliers that say, okay, this is maybe something different. And you can also have something like an outlier cluster. This is okay, it's not in our two model clusters, but there's a lot of information here. And this could be normal, or this could be an attack, you don't know at that point. The good thing is you don't need to define what your attacker needs to do. So in case of, for example, the signature, you really need to define this is the attack, and we can detect this. And here the idea is that we only see what's normal, and then anything that deviates from that is actually an attack. And in principle, this means that you can detect attacks that are normal, because of course, if something happens that is not normal, but you don't know what it is, you should actually be able to detect it. If you consider a system that does it like this, it could look like this. So here's your network. Again, with some probes that extract all your relevant data. Then you have some central processing here that extracts the correct events that are either no attacks, so they're labeled as normal, and your events with attacks. Then here would be this learning phase where you take all this data that is labeled as normal, learn some kind of model or derived model, and you have this model, and then you can use it in the analysis subsystem to just take your new events that happen, compare them with the model, see what happens, and can detect an abnormal event. Challenge, as I said, that's basically again the slide I'm a little bit skipping here. I think every possible normal behavior is not really possible, especially if humans are involved. And if you have something that's very close to a boundary, so if you imagine here, it's sometimes hard to say, is it now abnormal or is it normal? And because all this is highly statistical, sometimes you have these outliers that are very close outliers, and there it can be very difficult to actually decide what this is now. In the end, this kind of also requires that the attacker again acts the same way every time, because then of course if the attacker somehow is basically detected once, he has to be dynamic to evade the next time, and often the attackers do that themselves anyway, so an attacker usually don't use the same techniques every time once they are in a network, because they are feared of being detected. And so they are, even if you maybe detect it the first time, you might not detect it the second time because they adapt. And you have some false negatives there. And this even makes the process of defining normal behavior more difficult because the attacker can constantly adapt. And usually the consensus in, especially in our group and in Hamburg, but also generally in the security community, is that it's not really possible to define normal behavior in a static way, and it evolves over time, and this makes it very hard for anomaly-based detection to work, actually. Also, the question is, what does an anomaly even mean? In security context, you can say, okay, every anomaly is an attack, but that usually is not the case. Sometimes an anomaly is just an anomaly, maybe something that is not planned. Only happens once a month, so if your maintenance only happens at the end of the month and your training data is only in the middle of the month, then you of course cannot expect this activity to happen. And the problem is often that you cannot really take existing approaches from other anomaly detection areas, because every time the semantics are different. You just cannot take this approach and say, okay, every anomaly is bad. We know this from, I don't know, bioinformatics. Let's just apply it in IT security. Usually it doesn't work, because you have different domains, different requirements, and you have to adapt somehow. And of course, the last one that's actually also very important, you don't usually have labeled data, because if you remember the picture, there was this one arrow that says attack or event without attacks, and usually you don't even know what this stream is, and you don't know a certain time where you're 100% certain that there has been no attack. So obtaining an accurate and representative labeled data set is really expensive, and then you actually normally have a human that looks at some data and says, okay, that is malicious or not. Of course, that can also be error prone, so it's really hard to obtain labeled data. And also sometimes, okay, you can label something, but you just have noise, so something that happens in the background. This can also diminish the quality of your data set. And the last one, when you label this data that you're actually using to derive the model, that can have privacy implications, because, for example, if you then your model includes this thing that every time after lunchtime your employee watch the YouTube video because he has to get back to his working habit maybe. That's some habit that can maybe then used against him by the employer. So you really include some work-related or personal habits in there, and that's usually a privacy concern if you're thinking about this. What methods can we use? So there is usually the algorithms are actually the same as in other domains. So you can do something like neighbor-based, nearest neighbor-based anomaly detection. So k-nearest neighbors or something like that. And here the assumption is, if we think back to our image, the normal data points that we have occur in dense neighborhoods. So you have clusters that are really close together, and anomalies are more or less on the outside. You need to have some kind of distance function that depends on how you actually derive your access values, and the algorithm you would then use is something like k-nearest neighbors. And if you look at this here, of course, if you have a new example that you want to classify, and your k-nearest neighbors algorithm selected this cluster, then you would of course assign it to a cluster. But for example, in this example, it's very hard to decide to which cluster it should belong, because the difference or the distance here is very similar. And this is this problem that I talked about earlier. If you have something, it's very hard to either assign it a cluster at all, or say is it anomalous or not, or if you know it is definitely normal, which cluster does it belong to. The good thing here is usually that it's unsupervised, because you don't label the data beforehand. You just say, okay, we do k-nearest neighbors, we define k, and you get the clusters by yourself, and then you can afterwards look at the clusters and say, okay, is class A malicious or is class B malicious, or maybe none of them are malicious. And it can also adapt to different data types, so you don't you can throw anything in you want. You just have to know some distance function between the points to make sense of this data. Of course, that also means the performance heavily relies on that. If you do some really complex calculations to compare two points, then this is very resource expensive. Depending on all the parameters, depending on how you choose k, depending on how you choose your distance function, depending on how you actually, how good your data is, how much noise there is, you could have, or you usually have, high false positive ratio, because you don't actually know in which cluster you are, or you have clusters that basically shouldn't be there because they are noise, and then you have a lot of false positives that look malicious, but they're actually not. You could also have something like classification-based anomaly detection. That would be more the classical approach. You learn a model and then you test for it. There you have your usual machine learning techniques. You have something like neural networks. You also have Bayesian networks. That's something that I'm actually working on a little bit right now. Or something like support vector machines, similar technique there. Good thing here is that once you learn your model, testing is very fast. You can just through neural network edit, it can classify very, very easily. But again, this is the problems that we previously highlighted. You have to have accurate labeled data, and this is usually why these approaches are not used that often. And of course, there are many more methods which you can use. It was just a highlight of two new ones. You can do clustering-based things. Actually, we have some publications in this area. You can do statistical anomaly detection, information theoretic anomaly detection, or even spectral anomaly detection. All different things where there exist some papers. The other two ones are really the most prominent ones. So what are problems of intrusion detection systems? To kind of come back a little bit, we now see how intrusion detection works usually, some requirements that we have for it, what are problems. So usually, as said earlier, the amount of log data is very, very, very large. So you need significant storage capacities. If you not only do real time, if you want to also go back and sometimes look what happened previously, all this data needs to be stored. And you need to have really high performance automated processing to handle all this data that comes in. The question is also should all the data be stored? So should it be stored on a log server? Then you need to transfer it there. Should it be stored on the host? Then of course the host gets used more and more. And also this might prove difficult if an attacker can modify the data that is stored on the host, for example. So that's also not optimal. Then all the data should be protected. So as I just said, if your system gets compromised, the audit data should not be also compromised. And if you use the log server, then yeah, if your log server gets compromised, then you also have problems. And then also the question of expressiveness, so which information do you actually need? Especially if you have your host monitoring and you log all this data, and you don't know beforehand what is relevant, then you have this huge amounts of data which you then first have to filter or make sense of. And this usually leads to the fact that the orders that are actually stored, because you want to keep low volume, they actually only contain a low percentage of useful information. And would you have known better beforehand, it would have been more, but they didn't know, so it's a lot of data is lost there. Also privacy, as mentioned before, is a big problem, because you log something like user IDs, process names, also something like directories, or yeah, basically combinations of these two, of all these elements, result in big privacy implications. So if you log that every time your user opens any process, then again this can be used to build habits, and that's bad, not only in the anomaly based parts, but in every IDS. So there are ways to anonymize this, but at first it's a problem, and especially if you have to perform an audit that may violate the privacy of users. Also, this information might be abused, so if someone that has access to this audit data that's not allowed to access this, for example, if you can see in this audit data what your colleague does every afternoon, for example, and this is of course also a violation and should be prohibited. And ways which you can, or a potential solution is kind of something like a pseudonymous audit. So you replace every ID that is directly identifying with a certain pseudonym. That could also be done for processes, for example, and only if you detect an incident, so if you really see, okay, something is wrong with that host, there might have been an application, then you can basically use your mapping that you have stored somewhere else securely to see, okay, which pseudonym does this user, or which user does this pseudonym belong to, and then you can basically go further and really identify the user account that is responsible for this incident. So that's kind of a little bit of privacy gain. Another problem is also the analysis. So you usually have the problem that the efficiency is not perfect, especially if you're in a distributed scenario. Each agent does partial evaluation, and that sometimes is not really efficient. Although if you do the central analysis, then you have this performance bottleneck that is reported to the central point. So it's also not great, and that's especially bad if you have really sophisticated attacks that use different hosts, that attack different subnets, that use different applications. And if you then are in a distributed IDS scenario, the efficiency can degrade a little bit. And usually, as I said earlier, we don't want to have false positives, but usually we have a lot of false positives. And actually, if you just start Zeek in your default configuration, it produces a lot of just, oh, this might be bad alerts. And depending on your network size, depending on your configuration, this can easily exceed something like 10,000 a month. And you can just imagine if you divide 10,000 by 30, and you get that every day as a security admin. That's really tiring, and that's also not efficient anymore because you can't handle all these alerts. Of course, there are again countermeasures, so you can do, based on the intrusion detection, you can then do alert correlation. That's the next step. You then correlate alerts together and then make sets of them in a clustered way. But yeah, that's not really covered here. And some other problems. So again, self-protection is a problem. You do not want your IDS to be attacked by some insider attackers. You need to have strategies to cope with high load. If a lot of data is produced, high number of false positives. Okay, that's wicked here. And also cooperation between multiple IDS. So this distributed part is not really solved right now. And of course, distributed attacks that produce many alerts that belong to the same attack have to be detected together. So if you have a distributed port scan, so you have multiple machines that are controlled by the same attacker, that each, for example, scan a single port, then maybe each single scan does not look suspicious, but all scans together are actually dangerous. And if to detect this, you really need to have multiple IDSs that work together and detect this. So, there's a lot of content, I know. To sum up, you can classify or you can apply taxonomy to IDSs, so you can distinguish between host and network based or hybrid. You can distinguish between signature based, policy based, and anomaly based, and you can also distinguish between passive and active monitoring. So we just have seen passive monitoring up until now. You can also there's collaborative IDS, which is the trend. Here you are focusing on detection of large-scale and coordinated attacks. You can again differentiate between centralized, hierarchical, and distributed. Alert correlation is still a major challenge, and that's also why we're in our group working on that. And there are evasion attacks to bypass IDS. I've not covered this explicitly, but if you, for example, modify your signature just a little bit and your signature is too narrow, then you won't get detected anymore. It's especially the case for antivirus software, and that's why also the databases are so large, because they have to cover every variation of the signature. And via cover channel attacks, for example, you can also evade basically anomaly based detection. So 2 more slides and then we're done, I think. A really short part to honeypots. So if you're back to the whole picture, we've now covered this part also somehow. What about honeypots? So these are, as on the previous slide mentioned, an active way of detecting attackers. If you want to define it in one sentence, it's basically a security resource whose value lies in being probed, attacked, or compromised. So it's a resource that doesn't provide any value by itself. There's no production database, there's no production value inside it. It's only there so an attacker accesses it and basically generates an alert. So the idea is you want to get this honeypot compromised. You want to have someone attack it. But of course it cannot be a standalone security mechanism. So if an attacker sees that this is a honeypot, just doesn't attack it, then you don't see it. So you need to have a combination of your regular intrusion detection system and maybe also some honeypots that are supporting your intrusion detection. So why should we do this? The first one is fun, and that's actually meant as it said there. We actually developed our own honeypot in our group, and it's really fun to just look at what stupid combinations people use on the internet. So if you just put a honeypot on the open internet, you see, I don't know, usually sometimes between 5,000 and 10,000 login attempts every day of people that try out random combinations, and that can be fun to monitor. The good thing also is there's no false positives, because a honeypot is only there to be attacked, and no normal user will ever use it. So if someone connects with this honeypot, it's by default already something that's potentially dangerous. So you don't have any false positives. You can also use it for research. You can use it from malware analysis or reverse engineering. So if someone uploads a file, if someone connects to the honeypot, uploads a malicious file, a malware file, the honeypot can then download this, save it, maybe do some analysis on that. There are even ways to do automated reverse engineering, but you can really gain some intelligence about what malware is used in the wild. And it can also be an early warning system, because you maybe see some new attacks that are just popping up, scanning the internet, and one is then hitting the honeypot, and you see what the attacker is actually doing, which scripts they execute, and so on. Advantages are basically the data sets are smaller, because you only see people that actually connect to it. You don't see all the other noise in your network. They are highly flexible, because you can really configure them, which protocols should they support, should they handle malware, should they not handle malware. All these configurations are possible. There's also a lot of tools out there, so we have our own, but there are also a lot of open source ones. As I said, no false positives. Potential to catch false negatives, so something that your usual IDS does not detect because it doesn't know about it, can be caught by a honeypot if you're lucky. And usually it is a low overhead, because it doesn't need many resources. You can just put it on a small machine and you're done. Drawbacks, of course, is one, the limited visibility. So if an attacker sees beforehand this is a honeypot and just scans it once and says, okay, probably honeypot, and never attacks it again, you don't see that, and you don't see the attacker doing something else. And also it's a potential additional attack surface. If your honeypot gets compromised, that's just a host in your network, right? So if that is compromised and maybe the honeypot is coded badly, then the attacker has already foothold in the network. And actually the resource that we wanted to use as a security mechanism then becomes the attack vector, so to say. And yeah, there's a balance between these advantages and drawbacks. That's why you have to consider both and see if it makes sense to just deploy a honeypot. We in our university also host one, and that's very interesting. So, the overall summary, there's both IDS and honeypots are reactive security tools to detect attacks and react to them. IDS, you have all this taxonomy, I won't repeat that again. Classification depends on how many sensors you have deployed, how sophisticated the attack is, how good your algorithms are, and all that. There are problems because you have huge data to process, you have limited accuracy, usually, and a large number of false positives. There's privacy implications that I've talked about, and there's techniques to evade an IDS. And honeypots can be purely or also somehow active. It's purely passive, it's not 100% true, but it can also be an additional monitoring component where there are maybe more false positives because it's by definition something that wants to get attacked. So that's it. And actually I'm giving you the time, so if you have any questions then feel free to ask me. Should we do the microphone or
I can just speak.
Okay.
So just, I work in this field, so I know that it's very difficult to get labeled data. So the question is actually what data do you use or have you been using?
Actually we are not really using much anomaly detection, so because of this reason, because we don't have the data set, we don't do a lot of anomaly detection. There are some limited data sets out there, a lot of them are really outdated, so something from 98 or 2001 or something, which are labeled according to, for example, this is a DDoS attack, these packets belong to DDoS attack, these belong to something else. And these are usually also the ones that a publication uses in this field. But as I said, for me personally, that's not really convincing if you've used a data set from 20 years ago, because of course attacks are shifting and different now. But sometimes you also have publications that say we have a data set obtained internally, somehow we don't give it to you and trust us. And so it's bad. It's a problem, and that's why also we don't do a lot of research in this area. So no good answer there, unfortunately.
The Canadian Security Agency actually has some data which my student is using. I'm actually working with a professor at the University of Bremen, similar things. So
okay. Yeah. Any other questions?
Okay, I have a question.
Yeah.
In your presentation, you show 3 types of detection system, like policy based, anomaly based, and another is signature based.
Yeah.
So in the anomaly based, if we use the machine learning, then the target is 2. One is anomaly and one is normal. 2 types of data. So if there is more than 2 types of classes, like if we want to detect more types of anomaly, like DOS, probe, and then there are more than 2. So is it one types of anomaly based, or it is another types?
I mean, it depends on what IES and what technique you're using. So it doesn't just the classification of saying, okay, this is anomaly based does not mean there can only be 2 classes. So we have also algorithms that do something, especially like something clustering based, that do exactly what you just said. They do something like we take all this NetFlow data, or not NetFlow, but this communication data, we build a communication graph, and then we label clusters according to DOS, worm, something else. That would also be counted in that area. But again, then it usually, the problem is, okay, you need to define what clusters you have beforehand. It's very hard to do something that says, okay, that's unsupervised, that just uses unlabeled data and says, okay, we just cluster it, and this is cluster A, and this is cluster B, and this is cluster C, but then you don't know what that is. So we actually have one publication in this area that just takes a random data set that is not labeled and does some clustering on that, and then we have some argumentation why the clustering makes sense. But there's no formal proof that we say, okay, this is labeled and we detected it exactly like this, and this is why our accuracy is this good. So we more or less argue why it's correct, and yeah, that's basically the problem because of these unsupervised approaches. So it depends. You can do both, and both would be in the taxonomy. Both would be anomaly based. It's just a matter of do you do anomaly not anomaly, or do you do normal anomaly type 1, which means DDoS, anomaly type 2, which means something else. Yeah, it differs.
One more maybe. Are you aware of any real-time clustering methods where you mentioned the k nearest neighbors, you have to set k for the number of clusters? Are there any algorithms where you don't have to preset the number of clusters? I mean, leading on from this question, where the number can be defined in real time.
I mean, you can use something. Depends on what you mean with real time. I mean, there's something you can use something like dbScan, which requires some other parameters, of course, but it still can detect a varying number of clusters. But you then have to, yeah, as you probably know, define the distance and stuff. So I'm not aware of something that's completely free of these parameters. But yeah, usually all this analysis is done afterwards in not real time anyway. So the things that we do, the clustering, is also just take this data set, ingest it all, and then do it. There's no live clustering of, okay, we have new events now. And usually it doesn't matter if you use k-nearest neighbors or dbScan or something else. Usually all publications do it post-mortem, so to say, and just take all the data and then do it. So no, I'm not aware of those algorithms.
So what is actually the main rule of machine learning? Is actually only the offline classification, or it is the system or prevention or detection system? Interface sequentially can be machine learning, or detection is can be machine learning system, or only data, the connect data and classify the system?
So that's actually correct. I mean, machine learning is just a tool that you use for intrusion detection, right? So if you just say, okay, we want to do anomaly-based intrusion detection, then you can use these machine learning approaches like neural networks, like clustering, like whatever, and then it's basically, yeah, used for this purpose. But of course, as IT security is a specific domain, you need to know what the results mean, and so it's not, yeah, it's not necessarily tied to it. It's just a tool that you use. So I mean, machine learning itself, I would not put on any circle because it's something different. You can just use it alone. But if you want to use it for intrusion detection, then it's usually something in the detection part, because you take all the data, learn something, and then say, okay, I detected something. So does that answer the question, or did you need something else?
So, excuse me, thank you very much for your nice presentation. So detection actually after attack, right? Detection. So if we want to detect attack, there are three mechanisms: signature, policy, and anomaly. Actually you right? So which one is most fast? About computational time.
Yeah, usually anomaly based is very fast once you have learned the model, because you can then just check it, and the classification part is very fast. Training can be a little bit more intensive. Yeah, policy based and signature based are usually a little bit more intensive, because if you have a very large database of signatures, then you of course need to check your packet against all these signatures. So there are ways to make this fast, and Snort is still able to do real time, but it uses some CPU, not few, so a lot of CPU actually. So I would say from a computational standpoint, then probably this anomaly based stuff is the fastest.
Thank you.